All right, we're going to talk about angles and radian measure today. So first thing is understanding what standard position, initial side, terminal side, that type of vocabulary is. So in trig, you're going to be using what's called a unit circle quite a bit, and what we do is we take an angle or a ray that's attached at the origin of a coordinate plane, and that lies on the positive x side of the or the positive side of the x-axis, and then that's your initial starting position. Okay, this is called standard position when you actually start right here. So this would be like our initial side of an angle. So the initial side is the starting side of an angle formed by rotating a ray, usually counterclockwise. So we're going to rotate this ray counterclockwise, and where that ray ends, it sweeps out an angle. Right? So now you have an angle right here from our initial to what's called our terminal side. All right, the terminal side is that's the ending side of an angle formed by rotating the ray. The standard position is when an angle's vertex is at the origin and its initial side is on the x-axis, and it's on the positive side of the x-axis. Okay, you think positive side there. Okay, one other thing I just want to point out, if we were rotating here, when your angle's just lying here and nothing's happening, you're at 0 degrees. When you go all the way, if you were to rotate all the way up to this y-axis, you're at 90 degrees. And if you keep rotating, you'd be at 180 degrees. You kept rotating there. From there, you go another 90, which would be 180 plus 90, or 18 plus 9 is 270, right? 27, 270. And then if you kept rotating from there, you'd end up at 360, which actually happens to be at 0 again, right? And you could keep going. Another rotation wouldn't bring you to 90. I mean, it would bring you to the 90-degree angle, but it actually bring you to 360 plus 90, or 450, and then 540, and then 630, and then 720, and you just keep going around and around in circles. Okay? So let's go ahead and draw some angles with the given measure in standard position. So you're going to see that in standard position a lot. That just means, hey, start with your angle right here. So starting there, rotating 130 degrees, well, 90 degrees we know is right there. 180 is over here. Well, or in between 90 and 180 is actually a 45, right? So if you add 45, you're at 135. Well, 130 is just before that. I'm going to estimate, I'm going to say it's about right there. Okay, that's a 130-degree angle. 245, well, once again, you start in standard position. You rotate. There's 90. There's 180. There's 270. Uh-oh, went too far, right? Okay, 90, 180. Well, you don't go to here. That's 270. In between 180 and 270, well, you add 45 again, that's 225. Well, that's a little more than halfway. Okay, so we're going to say that's about 245. 620, well, notice 620 is over 360, so you actually have to go all the way around at least once. There's 360. Count by 936, 45 or 450. Keep going. 540. Keep going. The next one would be 63 or 630, so it's right before that. About right there. 620. And the answer is yes, you have to do the big circle like that. That shows how many times you've rotated around. So you're lucky I didn't say like 1,000 or 3,000 degrees, because you just keep going, driving or rolling around in circles there. Well, notice a negative angle from standard position doesn't go counterclockwise. It actually goes clockwise. So 75 isn't quite 90. It goes about there. That's a 75-degree angle. in the negative style. So that would be negative 75. Negative goes downward to begin with, or actually deals with going clockwise, if you want to think of it that way. Okay. All right. Well, let's go ahead and move on. So one other thing about angles, coterminal. Co meaning together, terminal meaning they terminate, they end. Okay. So when terminal sides are the same, they are coterminal. Okay, so if I had an angle, say, starts right here, right? And, well, let's kind of deal with this. Let's say I go 270 degrees. Okay. There's 270. Well, a coterminal from there, to get back to that spot, I'd have to, let me go ahead and switch colors. I'd have to go around from here and keep going. To get back here, I'd have to go around one time, or I'd have to go around another 360, or 270, plus 360. So when I add a whole rotation there, I'm now at 630 degrees, right? Okay, I'm now at a coterminal angle. So 630 and 270, those are coterminal. They end in the same spot. All right. So really, if you need to find a coterminal angle, you could just add 360 to it. We could have also subtracted 360, right? Like if I wanted to go a different route, I could have said, well, what if I want to go the other way? So I'm at 270. I want to go this way. Well, you can go backwards 360. So if I'm at 270 and I subtract 360, well, a coterminal angle would be, that would be a negative 90. So negative 90 degrees is coterminal. Okay? And the way we showed that, we wouldn't actually show it with that line. We just say this way. Negative 90. That's coterminal. It ends in the same spot. Okay, and actually the 631 would actually, we'd have to make it the entire, it would be like the same rotation there, the same color. So find one positive angle and one negative angle that are coterminal with the following. So if I have a 45, we don't have to draw it out. You could just add 360. 45 plus 360. That will be coterminal. Just one more rotation. Would that be? Well, that would be 405 degrees. I mean, there's an infinite number of possibilities. You can keep adding 360 and get an infinite number of coterminal angles because this data is called periodic. It keeps going on and on forever. And we could go at negative 45, and I could subtract 360. That would give you my negative one, right? That's going to give me negative 315 degrees. That would be the first negative coterminal, first positive coterminal. Okay? So if I'm dealing with a positive coterminal for negative 50, well, a negative 50 plus 360, well, that's 310 degrees. Or I could go negative 50, and I could subtract 360. All right? That would give me negative 410 degrees. All right? Well, 430 degree angle. Well, I could go 430 minus 360. That's going to give me well, in this case, that's 70 degrees. Well, that's a positive coterminal. If I want a negative, I have to keep going. I have to go 70 minus 360. I have to go one more rotation. In that case, it's negative 290 degrees. So now I have a negative and a positive. And notice subtracting still gave me a positive because I was over 360. So a positive and a negative. All right. Let's go ahead and move on here. Some vocabulary. Talk about some radians. A radian, it's different than a degree, but a radian, the measure of an angle in standard position, whose terminal side intercepts an arc length that is the same length as the radius. That's why we call it a radian. Okay? And so if I were to say, like, look at this right here, this length right here, if I were to take that length r and I was to stretch it, I was able to bend it and stretch it along a circle like that, that would be, oops, about that, that would be a radian. There's that same length. Now this is an estimate, but okay. So each one of these is a length of r. All right, and then I have this little chunk left over here. That is not a length of r. I'll explain what that is here in a minute, but we still have to count it, right? So it looks like we have 1, 2, 3, 4, 5, 6, and a little more radians in, well, that's 360 degrees. So I'm going to kind of estimate it. It's going to say about 6 1/4, 6.25, and I'm actually going to put the kind of rounded amount there. 6.28 is what it is. I'll explain how we get that here in a minute. And 180 degrees, well, that would be half of 6.28, which is about 3.14, which some of you may recognize as that cool number we call pi. So notice we're at 1, 2, 3, and then just this little chunk here. It's about 3.14. Okay, well, the way we could figure this out, actually, this outside rim in a circle, like the perimeter of a circle, is called our circumference. The circumference of a circle is equal to pi d, or 2 pi r. All right? And I'm going to use capital R because I used that here. Okay, but usually be lowercase r. Okay, 2 pi r. And if I want to know how many r's, this is the r we're talking about, how many r's there are in the circumference, you would have to take the circumference and divide it by the number of r's. Or, in this case, rather than using c, use this. Take that and divide it by r. And notice what happens. r's cancel. There are 2 pi radiuses in a circle. And that's in any circle. There are 2 pi radiuses. So 360 degrees has 2 pi radiuses. And we don't call them radiuses, we call them radians. But really it means there are 2 pi radiuses, which is about 6.28, right? 2 times pi is 6.28, rounded. Well, that means half of that, half of 2 pi, or half of 360 is 180, so half of 2 pi is pi. Well, and we know pi is approximately, rounded, is 3.14. And this is the relationship we generally use. 180 degrees is equal to pi radians. Okay? And on your calculator, there's a button that says R or rad, or if you go to the mode and switch between degrees and radians, when you're measuring in radians, you'll see pi, or you won't see a degree symbol. If you're measuring in degrees, you see a degree symbol. Okay? So to convert between degrees and radians, you're not going to do that on your calculator per se. You're going to take and use the ratio pi over 180. Now you'll see multiple versions of this. Some people will say 180 over pi. Some people say pi over 180. Some people will say 2 pi over 360. Some will make you use 2 different ones. Really, you can use this ratio always. Okay? Just understand that on top, you're dealing with radians. And on bottom, then, you're dealing with degrees. Wherever you put the 180, that's your degree. Wherever you put the pi, that's your radian. If you choose to switch it upside down, then fine. Then degrees would be on top, radians on bottom. But if I'm converting each degree measure to radians and each radian measure to degree down here, what I want to do is I want to look at this and go, okay, I have 60 degrees. And I want to change 60 into radians. Okay? So I'm going to use R for radians. Okay? Well, the ratio I use is, in this case, I'm going to go 180 over pi, right? Because my degrees are on top. Or if you wanted to use that exact ratio up there, that's fine. You can do it that way. You can say, well, pi over 180 is equal to, well, notice my radians are now on top, so r over my degrees that they give me, 60. How do you deal with a proportion? Well, you cross multiply. 60 pi is equal to 180r. You want to solve for radians r, so you divide both sides by 180. So you get 60 pi over 180, and you're not going to round it. You're just going to reduce it. How many what goes into 60 and 180? Well, 30 does. 60 does as well. 60 goes into 60 once. 60 goes into 180 3 times. So I get pi over 3. So here, r equals pi over 3. There are pi over 3 radians. Okay, 60 degrees is the same thing as pi over 3. And that will be a measurement that when we deal with the unit circle, you will memorize. Okay. All right, negative 135. So let's go ahead and hopefully you pause these and try it, but I'm just going to write it out. Pi over 180. Okay, notice my radians are on top, so I'm changing degrees to radians. So radians, there's my variable, and negative 135. Cross multiply, negative 135 times pi. 180 times r. Get r by itself by dividing by 180. So in that case, r is, well, we got to reduce what goes into 135 and 180. Well, I believe 9 does. Yeah, 9 goes, actually, 45 does. 45 goes into 135. It goes in 3 times. We keep the pi. And 45 goes into 180 4 times. Negative 3 pi over 4. Once again, that will be 3 pi over 4 is another one you will study. All right, let's try the next one here. Pi over 8. Well, that is notice pi, that's a radian measure. I need to switch this one to degrees. I'm still using the same ratio, pi over 180. It's just now I know the radians. So radians go on top, divided by my degrees. I'm trying to find the degrees now. Okay. And one thing you can do, anytime you have a fraction on top in the numerator, whatever's down here can actually slide to the bottom. We can show that mathematically, but it does happen. So you could actually write that as pi over 180 is equal to pi over 8d. And notice since your numerators are the same, you could cross multiply and solve, but when your numerators are the same, or your denominators are the same, you just set the other equal to you. So if numerators are the same, the denominators have to be equal. So that means you could just solve 180 equals 8d. Divide by 8. D is equal to 180 divided by 8, which is 22.5. That's 22.5 degrees. Same idea over here. Pi over 180 equals 3 pi over 4 over degrees. Hopefully you're pausing and trying these. Remember what I said, if you have a fraction in the numerator, that denominator can drop down and go pi over 180 is actually equal to 3 pi over 4d. And if you're good with fractions, there's a lot of things you could do here, but I'm just going to cross multiply. So 4d pi, or it's actually written as 4 pi d. 4 times pi times the degrees is equal to 180 times 3. Well, 180 times 3 is 540. And we have pi. Now you want to divide out the 4 pi. So your diameter is going to be 540 pi divided by 4 pi. And note what happens here. Pi's cancel. .540 divided by 4, well, that's 270 and then 135. So D here equals 135. And you could have saved yourself a lot of time if you recognized, and I know one kid in class today did, he said something to me. Okay, Jordan did. He said, hey, when he did this problem, he said, hold on, if this is negative 3 pi over 4, if that's negative 135, isn't 3 pi over 4 just going to be positive 135? And the answer is yes. So there you go. All right, one more here. We have pi over 180 equals negative pi over 6 over degrees. All right, once again, you can move that down. Okay, so it could be pi over 180 equals pi over negative 6d. Now you'll notice I brought the negative down with it because now I have denominators exactly the same. So I could just say numerators exactly the same. So I could say 180 has to equal negative 6d. And if that's the case, divide 180 by negative 6, d is equal to negative 30 degrees. Another one you will be memorizing. All right. We only got one more little piece here, okay, and talking about arc lengths and area of a sector. So the arc length S and the area of sector A with a radius R and the central angle theta, remember theta, is going to be measured in radians. To actually find that, and what we're talking about here, just so we know, we have a radius, okay, we have actually another radius, and we have theta, okay, so what we're doing is we're looking for arc length S. This is S right here. In fact, rather than using that, let's switch up the colors here. Here's the arc length. Okay, now it's actually a measurement, right? We're actually measuring a length, not a degree measure, okay? And not a radian measure. Here is the area, the inside of the sector, right? So we're talking about all this stuff in here, this little triangular shape. That is the area, right? Including the angle there. So we have area and we have arc length. Okay, so the arc length S and the area. So the area is equal to 1/2 r squared theta. The arc length, switch back to that color, is equal to r theta. Now notice what we're saying there. We're saying the length of the radius times whatever portion of the circle you're dealing with is equal to your arc length, right? Because the radius is directly tied to a piece of the perimeter when we're measuring in radians. So, for instance, here, if we had, say, like let's just say, for the sake of this example, our radius is 12, okay, and theta is pi over 6. All right, what that would mean is if my radius is 12 and theta is pi over 6, that means I am taking 12 and I'm multiplying it by a portion, because you're saying that this length here, this radius is being measured along here. You're laying it down, but you're only taking a portion of it. The portion you're taking is pi over 6. Okay, and so in this case, pi over 6 gives me 12 pi over 6, which would be 2 pi. So the length of this arc would be 2 pi if the radius is 12. Okay, you only get a portion of it, right? 2 pi is about 6.28, so we only get a piece of that radius. We don't get the whole thing. It's not the entire length, because this length is different than this. But when you're measuring in radians, you're measuring based upon the length of your radius. Okay, and same thing with area. You're taking a piece of it. So let's use a different. Let's just show you how that formula comes up. We know that the area of a circle, when we I dealt with just a normal circle and not dealing with radians as pi r squared. That's the whole circle. If I wanted a piece of that circle, you learned in geometry you could just take this pi r squared to find a portion of it. Like if you wanted just a piece or a sector of it like this, you would multiply it by, you know, if they wanted 60 degrees of it, you'd say, well, 60 out of 360 times pi r squared, right? And that would help you to find your area of just that sector. Well, when you're dealing with radians, that pi r squared, it doesn't get multiplied by 60 over 360. It gets multiplied by whatever theta is over 2 pi. Remember, there's 2 pi radians in an entire circle. That's like your 360. And theta represents your angle measure. Okay, so when you go theta over 2 pi times pi r squared, notice I just extended that over, right? Because really when I say times pi r squared, well, making that in a fraction just gives me that. But note what happens here. And let's switch up some colors here. This cancels. Pi cancels. And I'm left with r squared times theta, and then all over 2. Well, another way of writing that is 1/2 r squared theta, which is this formula right here. So you just, looks a little different. It's stuff you've done in geometry, but you're dealing with radians now, so it's a bit different. So let's use that here. So find the arc length and area of the indicated sector. We're just going to try to practice these formulas here, okay? And so I'll just rewrite our formulas up here. You should have them. Whoop, excuse me. You can also reference that slide. The S is equal to r theta. That's our arc length. And area is equal to 1/2 r squared theta. Okay? And so find the arc length and area. Well, to find the arc length, so S in this case, I need to know the radius, and the radius is 14. So we have 14. And I need to know theta. Theta happens to be pi over 2. 14 times pi over 2, well, that's 14 pi over 2. Or if you reduce it, that is 7 pi. So the arc length, S, is 7 pi. Okay. If you rounded that, by the way, like if you multiplied it out, they wanted you to round it, it'd be about 22.0 centimeters. A lot of times they'll have you round that, so approximately that if you go out. Okay, your area, well, area is equal to 1/2 r squared theta. Well, in this case, r is 14 squared, theta is pi over 2. Okay, so that's equal to 1/2 of 196 times pi over 2. Okay, well, that's 1 times 196, right? And then 2's on the bottom. You can do some canceling or you do some reduce. Personally, just get rid of that 2, call this 98, get rid of that 2, and call this 49. So I end up with 49 pi. Okay? And 49 pi is about 153.9. All right. And that would be square centimeters. Okay. Well, let's try the next one here. I hope you pause it and give it a go on your own, but I'm going to go ahead and just work through it. S is equal to R, which is 13, times theta, which is 3 pi over 4. Multiply that. 3 times 13 is 39 times pi over 4. 39 pi over 4 is approximately, well, some technical difficulties. It is approximately 30.6. All right, so 2 different routes to write it there. And let's go ahead and switch to a color we're not using there. So area is equal to 1/2 our radius, which is 13, squared, times theta, which is 3 pi over 4. So we have 1/2 of 169 times 3 pi over 4, which is 1/2. Well, 1/2 of 169 times 3 pi over 4. So 1 times 169 times 3 pi is 504, or no, 507, excuse me, pi, all over 2 times 4, which is 8. And we're going to round that. That's going to be 199.1 square feet. All right. Well, that's all I got for you. Good lucky.